Right, hell yeah. One of my favorite subscribers commented on one of my videos. A lot of my videos, I start by, just the things in my head, what I was taught, what I thought I was taught, how I think things work. And just because technical definitions and proofs are rigorous and daunting, and sometimes they can lead to more confusion, where it's just fun to kind of use your intuition. But I am starting to kind of put together the pieces and actually use mathematical symbols as as a language. So if I use something like even just this symbol right here, this symbol right here is delta x. This is going to be a substantial change. This is different than dx. And so what I was trying to think about was the the definition of a definite integral. So when you take a definite integral, you're going to basically find, from a geometric perspective, the area under the curve from a lower limit to an upper limit. So you're going to have an integral sign, maybe with an a as your lower limit and a b as your upper limit. And I want to take, like this is kind of my whole thought, is just like, well, I just want to, and let me clarify. I wanted, because the integral sign is a summation sign, and very importantly, the Riemann sum is taking a curve and then evaluating it at a location and then giving that value a width. Now, that width and the height is going to be the area of a strip or a rectangle, and that is going to approximate the area under the curve. You're going to have some error there, but as we reduce the width of those rectangles, and effectively this is where that YouTuber was like, hey, that's where the number of rectangles goes to infinity. The number of rectangles is represented by the increment n. When you do a summation of n is equal to 1 to n is equal to 10 subsections. And so the Riemann sum to define a definite integral. And see, I'm just actually in the process of just trying to say correct things. But actually, I honestly despise saying correct things, because some of the top creators in the math and physics space, cool. They literally sound like an AI bot sometimes. You know what I mean? Or like, I was just watching one the other day, and they would just, when they said a correct thing, they would just emphasize it more, and it almost drives me crazy. Yeah. So enough said. But hell yeah. But as those sections, as you get a ton of them, and n goes to infinity, you're going to have an infinite number of slices. And the thing that got me confused was, you're actually, the width of those slices always is going to be the width between a and b, b minus a, and then divided by the number of slices. So that's kind of that part always, if I'm going to forget one thing, that's going to be that. So if I have one slice, it's just going to be b minus a. The width of that and the area under the curve, that's going to be the width evaluated at the first point. You're just going to, basically assume the thing is a rectangle or a square. And then once you get two intervals, you're going to have two slices. You might have a difference in height of the rectangles, and that's going to better approximate it. And as you get 10 subsections or slices, that you get closer, adding up those rectangles to getting closer to the true area under the curve. And that's where integral, what I'm learning, and what I learned today or even yesterday, because I had to look this up even last night, when I see the word limit, I was just assuming it's some sort of hand waving, it's some sort of approximation, something that you actually can't attain, but it's just so fascinating that it's the complete opposite. And this is the most useful tool, asking a question in Google to be like, I was just like, well, is the limit I kind of just asked it that, or ask it the opposite. Like, is the limit a very precise thing? And yes, so that's what I'm going to take going forward from that. Anytime I see the word limit, this has to be an exact value. You know what I mean? And so that's where I can show you my mistake right now. So I can show you my mistake, but I'm going to set up the Riemann sum. I'm going to take some curve, and I'm going to start at the value of a, and then I'm going to go to delta x. And so that's my value of b. But I also want my value of b to change, because I want delta x to go to 0. I'm actually going to take the limit. And see how I emphasize that? And you're supposed to be like, oh, he knows what he's talking about. But anyway, I'm going to take the limit as delta x goes to 0. And so, you know what I mean? Flash forward to the actual statement is that value is going to be 0. And that was really cool for that YouTuber to really comment on that. And I don't know if I could even fully understand his comment because I already have a mistake in perspective. And I haven't really even dived into the nuts and bolts of his comment because I would like to even take his comment and, write out the things that he's talking about in a mathematical way, like using expressions and seeing how those expressions, they're kind of like truth statements. And, and that's what I'm kind of getting at going back to the fundamentals, especially with calculus. If I have a equal sign, then what's on the left has to equal what's on the right. And those are powerful tools. But hell yeah. So if I take the limit as delta x goes to 0, guess what delta x is going to be? It is going to be 0, which means, and I should, kind of explain the Riemann sum. I'm going to have some sort of curve. I'm going to have a value where x is equal to a. So along the independent axis, I'm just going to choose some value a. And then when I plug that value into the function, this is the function, and what the fundamentals of a function is if I plug in one value, I get out one value. So if I plug in the independent variable where that value is a, then I'm going to get out only one singular value. And that means that this curve, from a graphical perspective, just doesn't overlap itself. If it did some sort of S shape like this, and I took this value at A, it might hit 2 to 3 locations. 3 locations in that example. Okay, so I have this value at A, and that's going to be the height of the function. And what I want to do is find the area under the curve of basically a dx. Because you have this integral sign, whether it's a definite integral or just kind of the integral sign in general. The integral sign is supposed to represent a sum, like the indefinite integral sign. We just have the integral sign. The lower limit is negative infinity. The upper limit is infinity. I'm going to have that. You'll see f of x. And then you're going to see a multiplied by dx. And it was that going into this week to be like, oh, well, that's a summation over, the entire region from negative infinity to infinity. I just want to find one slice. I want to find the smallest possible slice. And this is where we're ending the video. You know what I mean? Or this is the take-home point. I can't do it this way. And I haven't even thought about doing it in a different way. Yeah, I'll have to think because, yeah. So the take home on this is if I set the limit of delta x goes to 0, that interval shrinks to 0. It has to. And so that's what I learned from writing in to figuring out what the definition of a limit. This limit is a very hard exact value. And that's cool. I don't think I was ever taught that. I don't know what I was taught. You know what I mean? You see this word limit, and I think you just scratch your head and just move on with life until you get to a chapter where you no longer see that word no more. Okay, hell yeah. So that's it. This change in x goes to 0. There is no width to that interval. And so the area under the curve from a to delta x, where I was wanting it to represent a plus dx, you know what I mean? Some infinitesimally small change in x by representing change in x going to 0. Just because I'll have to look this up. I thought one of the definitions of dx was when delta x goes to 0. So I'm not going to do it for this video. Well, I mean, we could. Yeah, might as well. So let's go Google. And is dx not the same as delta, as the limit of delta x approaching 0? My hunch is that the limit is a very exact term. And so dx does not represent 0. It represents an infinitesimally small. It's the smallest width you can have, but it still has to have width. And that's where doing like subsections, like I want to make an infinite amount of subsections. So if I have if I have just like a very simple equation, y is equal to 1, it's going to be a horizontal line. I'm going to evaluate this from 1 to 0. The area under the curve is 1. And if I wanted to find that from sectioning that up, and if I did an infinite number of slices, well, there's going to be an infinite number of slices between 0 and 1. And then let's say I want to, figure out how many slices there are going to be between 0 and 0.1. Well, there's going to be an infinite number of slices. And there's always going to be an infinite number of slices between each subsection between A and B. I'm choosing A to be 0, B to be 1, but I could choose A to be 0, and I could choose B to be any delta x, some sort of different interval. And that's the kicker. In between those two intervals, I can put an infinite number of subsections. And then I'm going to, each width of those subsections, you have to be very cautious about this, is going to be the difference between A and B, so B minus A, that's the total width, divided by those number of subsections. And I think because infinity is not a number, and we think that 1 times infinity is the same as 2 times infinity, I don't know what to deal with that. I still, anytime I see the word dx and the word infinity, I still just, kind of hand wave in my brain that I don't really get it. You know what I mean? And I think that's good. I think you should always have that, especially if there's something that you can't tangibly reach. Like, hey, I'm gonna make a mathematical expression of something that's almost intangible. And maybe it is tangible and I'm just messing with my head to be like, nah. But no, I think dx being so small, it's infinitesimally small, that it's approaching 0, but still has some sort of width. That messes with me. And that's where I came down this rabbit hole. Is like, well, isn't dx just delta x as the limit of delta x goes to 0? And no, because that would be a hard 0. So let's see what this says. And I could just be also wrong here. So yes, you can think of delta x, dx, as the result of, dx as delta x getting infinitesimally small, approaching 0. But they aren't strictly the same thing, and that's good. Delta x is real. It's a small change, while dx, well, and I don't even think it's actually getting what I'm talking about. But yeah, represents an infinitesimally small, but not 0. And that's where that YouTuber was for sure spot on. Be like, hey, you can't set up a limit where delta x goes to 0, because then I think you physically give it a 0 quantity. And I don't think this really explains that. Let me just read it, I guess. Delta x is a real small change, while dx represents that infinitely small but not 0 quantity in calculus, a concept more formally handled through limits where delta x goes to 0. So I'll have to go research where these limits of delta x actually going to 0 exist and how that is related to dx. This, when delta x goes to 0, it seems like they're telling me that it's useful when taking the derivative of the change in y with respect to the change in x. Not that delta x equals the limit. So yeah, I think that's the important thing. I can have a change in y divided by a change in x. So yeah, so now I'm actually kind of learning to speak the language, because I've seen that you can have a legitimate change in y, and that's the first problem you get to. That's the slope of, if I have some sort of curve here and I want to find the exact slope at a point, what they say in the textbooks is you have to have two values for any tangible representation of the slope. You have to have two values to actually, from a geometric perspective, show you that that's the slope. But then what's born is calculus, where we can take a delta y, which is a definite change in the y height, that's your rise, and then a definite change in the x. And we can keep making this change in x smaller and smaller and smaller, and that's going to be an equation where delta x goes to 0 and is going to give you a value of delta y. So that is a legitimate thing. Things are going to cancel, and then you're still going to have a function. This is a function where your denominator is equal to 0. Seems like things are just going to blow up to always to infinity, but that's not the case, and I'll have to research that just even from simple cases where now if you take this is going to represent any sort of derivative. So if I have like x squared, the derivative of that's just going to boil down to 2x. And I don't have a lot of those in my wheelhouse to be like, oh yeah, I know exactly how to do that, because like I said, anytime I've seen this word limit, I'm just like, well, let's skip all this and get to the calculus stuff that just seems plug and chug. But yeah, this all seems like it requires proofs and I don't know, but yeah, so we're kind of boiling it down. So the take-home points from yesterday were like, heck yeah. Anytime I see this word limit, it's going to be a precise value. It's saying, yes, you're going to approach, you might have to use numerical methods to actually approach the value, and you might have to use numerical methods to even just get to figure out what that value is from an approximation. But then, a lot of problems might be obvious that value is actually approaching a hard stop number. And that's what I've kind of taken from yesterday's studies. Heck yeah. So let's read on. So in essence, this dx symbol is the symbolic result of the limit process applied to delta x, treating it as a singular entity. Treating it as a single entity, let's see what they say, not a ratio where both numerator and denominator become 0. In essence, dx is the symbolic result of the limit process applied to delta x. Treating it as a single entity, dx. So they're saying, not a ratio where both numerator and denominator become 0. Okay, hell yeah. So anyway, so I think I'm good there. Back to this. I'm going to evaluate a function at a, and then I want to find the area with a change in x. My value for b is going to be a plus delta x. That's what I have here, and I'm going to try to find the area under the curve of that as the limit as delta x goes to 0. But again, that delta x is going to have no width, and only height. Can't represent an area. Or it can represent an area of 0, so that goes to 0. All right, so heck yeah. So I think this was just a step in the right direction to be like, hey, this is a mathematical expression. What we learned is that if I see this word limit, hey, I'm going to be starting to think about exact values. And that's important. I think every time I saw this word limit, it was more just kind of like a wishy-washy thing, like a hand-waving gesture. I literally thought this limit was an approximation. I thought you would. Yeah, that's a huge mistake, I guess, and maybe just a mistake from just not being taught the fundamentals to be like, hey, yeah, you're going to be learning this, but here's some huge take-home points that, you know what I mean, 10, 20 years from now, if I see, and I don't know, I'm just making this up in my head from yesterday, being like, heck yeah, for the next week, I'm going to see, every time I see this word limit, I'm going to think exact value, and it seems like that's going to be very useful. Alright, so that's it for this video. Thanks for joining me. Booyah.